So just a brief review of what we did last time. So in the first lecture on path integrals, we constructed the path integral. Last lecture we discussed one example of the free particle and then discussed the quantum mechanical propagator and the semi-classical limit where the typical action scale associated with the typical path is much larger than h bar, and arrived at this semi-classical approximation for the propagator, which is given by, so the propagator, the quantum mechanical amplitude to propagate from a point qi to a point qf in time t can be expressed as a sum of all classical paths connecting initial and final coordinates in time t. And what you have to, so if there are more classical paths than one connecting this, then you have to sum over all. And what you sum is an exponential given by the purely imaginary increment I times the classical action associated with the classical path divided by h bar. So this is the phase factor. And then there is a prefactor which is from, so this is just a contribution in the path integral by substituting into the actual classical path. Now there's another contribution which is a so-called fluctuation determinant, which results from fluctuation, Gaussian fluctuations around the classical path. And this can actually be expressed, so we just confirmed this, we didn't derive this expression, but we confirmed it for the free particle. I'm still thinking to make an exercise to prove this, but it's more technical, so maybe one way is just to believe this, and we will confirm this for several examples. So if you do the integral over Gaussian fluctuations in the neighborhood of a classical path, you have the fluctuation determinant, which can be expressed as a second derivative of the classical action for the classical paths. And the derivation is with respect to the final and the initial coordinate, and you have a factor 1 over h bar, and this is the square root just from doing the Gaussian integral. So we said that in the semi-classical limit, where the typical action scale is large, we have in contribution from typical paths. However, there we have an incoherent contribution of path and path in the neighborhood because the action varies linearly with the fluctuations around the given reference path, which leads to a strong suppression due to an highly oscillatory factor. However, in the vicinity of classical paths, we saw that the linear fluctuations around the reference path vanished, and we only have in leading order the quadratic fluctuations, the Gaussian fluctuations. Then lead to a coherent sum. This is why we could remain with this expression, which then tells us like how to see how classical mechanics arises, because if we take h bar state to 0, then only the classical paths contribute. However, here's still a reminiscence from quantum mechanics, which is due to the Gaussian fluctuation. So we can think of in many problems where we're interested in, let's say, the probability to paths were not microscopic, but let's say mesoscopic or macroscopic probe, where the typical action associated with propagation from one end to the other end through the probe is actually larger than h bar. We can use this approximation, and crucial here is then that we don't have the contribution only from the classical path, but there's still quantum fluctuations around it. This means that we have the possibility that path, in a way, if there's two classical paths which are coming close to each other, you have fluctuations between them. So you have the possibility that, in a way, particle propagates from one to the other, and then this gives rise to interference. So this is then all kept in this exponential here. So just to make the statement again, if we then are interested in the probability, like this is what we measure in experiment, it's not amplitudes but probabilities, we have to square this. If there's more than one classical path, we see that squaring this, we don't get only the sum of the squares of this expression, but we also get the interference terms, okay? And one thing which would be maybe nice for you to do, and probably next week or the week after we do some exercise session, is just to try to see how you can understand Aharonov Bohm or the double slit experiment just using semi-classical approximation. So you start out from this, you're interested in the probability that the particle propagates from one. So you have there the case where you have two paths and then just see how the interference term arises and how this depends on a magnetic field, yeah? So you know, the double slit can buy magnetic field perpendicular to the two slits, and then you should see an interference pattern arise. So just maybe sit down and try to formulate the problem and try to solve it, and then we discuss this in the exercise. Now, what we want to do is, this lecture is again like in the last lecture, we did first just a computational first exercise, which was calculating the propagator for the free particle, and then this conceptual part is semi-classical approximation. So what we want to do in this lecture is again, like, let's say, do two things. So first we do a computational part, which is evaluate the quantum mechanical propagator for the harmonic oscillator problem, and then we do something conceptual, which is relating the path integral. So this is path integral, how it appears in quantum mechanics. Then we want to see how the path integral appears in quantum statistics. So make this relation clear. And the problem, so we first discussed is a computation problem. What is the quantum mechanical propagator for the harmonic oscillator? Well, actually, we don't really have to do the calculation because we already have the answer here. No, we said that this is a semi-classical approximation, but all we did to arrive here was to use to parameterize the path, and the path integral is some reference path and then fluctuations around it. If we take a reference path, a classical path, then the fluctuations around it just do not contain linear terms. So the starting term is a quadratic term in fluctuations. Now, if we are considering a quadratic problem in the sense that the operators that appear in the Hamiltonian are just quadratic in momentum and coordinates, then this means that, well, the Taylor expansion and fluctuations around some reference path stops after the quadratic order. So if we then look at the harmonic oscillator problem, well, there we have exactly a quadratic problem. So then the semi-classical approximation should be exact. But why do we do the exercises just to have one scene how to calculate this fluctuation determinant, okay? So this is the determinant of some, if you have a discretized problem, it's a matrix. However, in general, it can be some functional appearing. So we want to see how typically one calculates these fluctuation determinants. So this is an exercise, but of course we should just then see that we confirm this. And then the second part is the more conceptual part. So let's start then with the harmonic oscillator. So we have a Hamiltonian given by two contributions, which are both quadratic. So it's a quadratic problem. Now, just one comment still is why, I mean, we consider such a specific case where even the semi-classical approximation is exact, so why do we want to study here in detail quadratic problem? Well, these quadratic problems are very important because often they will serve as the starting point for our analysis. So we do not know how to do integrals if there's appearing our quartic terms or higher order terms. We just don't know how to do it, but we can always try to formulate some perturbation theory around then, like higher order terms correspond to interactions. Okay? You can always try to formulate a perturbation theory around the non-interacting problem. So this then would amount to knowing the quadratic problem well, and then do some perturbation theory in higher order terms. So this is always a very relevant problem because this often serves as a reference or starting point for higher or for more complicated problems. And then let's use our expression that we derived for the quantum mechanical propagator. So here I use the Lagrangian version, so we have two versions, Hamiltonian and the Lagrangian. It's kind of case. I think here it's simpler to use for the problem the Lagrangian version, which propagator as the integral of all the paths with the boundary conditions, and what we integrate is classical action of the given path divided by h bar. And so what we want to do is we want to now consider the action for the harmonic oscillator problem, and then parameterize these paths again like we did before. So I said, if we take some reference trajectory, we can do a Taylor expansion around it in the vicinity. If we take classical trajectories as reference points, it simplifies the problem because there's no linear term. So we first want to solve the classical problem of finding the classical solutions, and then parameterize Gaussian fluctuations around them, and then just integrate all the Gaussian fluctuations. So that's a problem. Okay, so the action here is given by integral t and half squared times m squared. Okay, so that's a problem. We want to calculate this, and as said, so the first step is to parameterize these paths. Okay, so we proceed in how many steps? Well, it's 3 steps. So first is we will parameterize the paths. Then we have to find so we have to identify the classical path. We have to parameterize fluctuations around the classical path. Then we have to write down the action here as a contribution from the classical path plus the fluctuations. The classical path, we can just give this factor, and then we have to calculate this here by integrating over the fluctuation. So this will be kind of a 3-step process. So then start. First part, parameterization of paths. So we take an arbitrary path and now write this as some classical path or a classical path with fluctuations around it. Now we do not need to have any assumption that eta is small, that the fluctuations are small. It's just a convenient way to parameterize it, because we know if we insert this here, well, this is quadratic, then this stops, the Taylor expansion stops after the quadratic order of eta, and the linear term will disappear. So we don't need to rely in some sense, like we did here, that eta is small. Okay? We're now, this is like classical path plus fluctuations. And then the first step is to identify the classical path. So, classical path. And we satisfy the classical equation of motion, meaning that they extremize the action. So this is, I mean, a simple problem. Already have solved this like a million of times. So we can write this as a linear combination of 2 contributions, sine omega t plus the cosine omega t. And now we have to fix the boundary conditions, which are, so we have to fix the constants with boundary conditions. So we have Q classical at 0 should be Q initial, and Q classical of t should be Q final. Okay? So if we insert this ansatz, we see that this doesn't contribute at t equals 0. So this immediately gives us that B is equal to Q initial. Okay? So we have solved one equation. Now the second equation will fix the second variable. So just insert here Q classical of t. So maybe make it more, we should call this t prime. So we set in b the value that we have for b. We set in, we have one equation which then fixes the one free variable. And if you do the algebra, you will find that a. So let's see. First, the simpler one, b is given by q initial, also q final, q initial, and a is given by more complicated expression, which is q final. Now we have divided by sine of omega of t, which is the time of propagation, okay? Because this is just from, so we have t prime equals to t, minus qi, and then we have the cotangent of omega t. Okay, so this is the values for A and B. So inserting these here, we have found the classical path. Okay, so this is just, I mean, going through the calculation, simple calculation. Still, let me write down the solution. So Q prime, combining everything, divide this is Q final, divided by sine omega t minus Q initial cotangent omega t times sine omega t prime plus Q initial cosine omega t prime. Okay, so it's not such a nice expression, but still handleable. So this is the classical reference trajectory. Now let's look at the fluctuations. And this is now in a way why we do the exercise to see how we calculate this fluctuation determinant. So the fluctuations now obey the following boundary conditions because the classical path already satisfies the boundary conditions imposed by the path integral. Then the fluctuations have the boundary conditions that eta of 0 and eta of tau should be 0. Okay, so we have these boundary conditions, and this then motivates us to express the etas in terms of the Fourier series. Okay, so this means we can express them as the sum over sines or cosines over discrete frequencies obeying these boundary conditions. Now, what have we gained from this? If we express eta of t prime as a series of Fourier components, discrete Fourier components, this means that the integral here, which will now, so the classical contribution we don't integrate over, it's just the exponential that we pull out, then we would still have the function integral over the fluctuations, eta of tau, okay? But if we do the Fourier transform and respect the boundary conditions, we have here, again, a high-dimensional integral just over the Fourier components. Okay, so this will then amount to a high-dimensional integral in the Rn, meaning that what we get here is then just a simple matrix. Okay, and this is why it's convenient to make the ansatz for the Fourier expansion. It's more or less clear. I think it also becomes more clear in the calculation itself. So we make Fourier expansion for the fluctuations. Eta t prime is given by a sum, infinite sum over Fourier coefficients, and then we have here sine omega n t prime, and we have the discrete frequencies omega n being Pn divided by t to satisfy these two boundary conditions. Okay, we have to be in 0, or we have to be multiples of p over t to be at t at tau prime equals to t again at 0. Okay, and now what I just meant there is, so you see we parameterize each trajectory parameterized by a discrete set of points. Okay. So what we can then just do is here the integral over all the coefficients I, okay, which, okay, it's not a fine, it's not in the Rn, but it's discrete points, and this will simplify the calculation. Okay, so this is First step, parametrization of path. Classical part, fluctuations. Classical path, we just found from solving the classical problem with boundary conditions. Fluctuations, we just used applying the boundary conditions. We will use a Fourier expansion. So the second part now is, let's look at the action itself. So the action consists of two contributions, which is a contribution from the classical path and then a contribution from the fluctuations. Again, in general, okay, maybe I'm restating everything a million times, but just to make it once more clear, like, we would now say that this here is classical plus eta. Now the action only contains this variable in squared, okay? Derivatives or itself, yeah? So this will then give terms where we have, which depend quadratically on the classical path, quadratically on eta, and we have the mixed terms. Now, well, these are the classical contributions, this will be the Gaussian fluctuation. What about this term? Well, vanishes because we're considering fluctuations around the classical path, so the linear deviations vanish. Okay, so this is why it's convenient to use this parametrization. So the action will consist of two contributions. One is the classical, and one is the Gaussian fluctuations. So let's write down the two contributions. Completely separate, and I just again write down the contribution from the classical action. So this is again not immediately clear, but in the end it's just a simple exercise. No? So what one has to do, one has to use a classical solution, insert it into the action, and if one does so, one will find the following expression for the classical action, for the classical path. Squared cotangent omega t minus by sine omega t. Okay? So it's just a matter of calculation to verify this. So you may want to do it, but there's nothing, I mean, very like conceptually challenging, whatever. So in the end, you only have to integrate like sine squares or cosine squares, or you immediately you get the classical solutions to simplify the problem already at the beginning. So you may want to verify this. So let's look at the more interesting contribution, which is the one from the fluctuations. So the classical action of fluctuations is now given by integral t prime m half and to square root minus omega squared. This is just inserting the classical fluctuation, and actually now becomes really visible why we did the Fourier expansion. And this is, we have two contributions. One involves the derivative, one involves the function itself. Now using the Fourier expansion means that we expanded the path in eigenfunctions of the differential operator here. Okay? So the only differential operator appearing here, so this is numbers, is the derivative. So if we expand to the Fourier expansion, we can substitute this operator by numbers, and then what we have is like a big sum over coefficients Rn, Gaussian integral over Rn, and they are weighted with numbers. And this is just doing then a simple Gaussian integral. So This is like always a problem. You have, in principle, here like some kind of operator, and of course one way to write down the determinant of an operator is to write it down as the product of the eigenvalues, so to change to an eigenbasis, and this is what we did here. So let me see if I should give details. I give like some details. Okay, or the question? No, I write it down. So maybe I'm boring you with this here, but still I decide to write it down. So what do? We use, as said, that this is eigenfunction. So if we take the derivative, we get here the cosine omega n t prime, and we get the omega n outside here. Now we have two contributions, so we get a double sum over n equals 1, blah blah blah, with an sine omega n, and then a sum from m equals 1 with sine omega m, or in this case cosine omega m. But then we have the integral over dt, still to do dt prime. So we have an integral over dt prime which contains cosine omega n t prime times cosine omega m t prime. And then we can just use the orthogonality of this function here, which means that this integral only contributes is omega n equals to omega n. Okay? So this will give us an overall sum over an squared, which is just saying that we use eigenfunctions that diagonalize this expression here. Okay, so I write down the following intermediate steps. So this is, if you take into account the normalization and everything, then you will find that this is given by npt squared. So this comes from the omega n of 1, and the other one would be omega m, but in the end I have to set them equal, so this is a p over n t squared. This is a normalization from once equal to orthogonality, and then an squared. And the second thing is, well, in a very similar way, if you look at the contribution from eta squared, the argument is the same. The only change is that we use the orthogonality of the signs, and we don't have this factor because this results from the derivative. No? So this will be just p half n equals 1 to infinity, and then an squared. Okay? And should I write down the orthogonality relation for the sine and cosine, or everyone knows what I'm talking about? Everyone knows, okay. So then, if we use these two relations, what we find is that this is given as prefactor t half, sum n equals 1 to infinity, and then we have m half n p over t squared, which is from the derivative, minus omega squared, and all this is the weight of a given Fourier component an. Okay? So this is completed step number 2. So we have found a good parametrization, we have figured out the actions, and now we can go to the propagator, which will mean insert these expressions into the action and do the final integral over fluctuations. Questions up to here, or? So this is third step in the program, actually write down the propagator. So we can pull out the contribution from the classical action. This doesn't depend on, this is just a constant, this is not anymore an integral variable, just a constant value. And then we have to multiply this still with the integral, which is now over the fluctuations. And the fluctuations we parameterize by the Fourier coefficients, and each Fourier coefficient has a Gaussian weight H bar 1 squared 1 minus omega np squared. So this is just inserting this here, and I did some reformulation of this. I pulled out this factor, and this is will become clear why it's convenient to do this. Now this is exactly the form that we said here. So we have the classical action. This is just now dealing with the fluctuation determinant. So we want to see how this gets calculated. So it's of the form classical action times some fluctuation determinant. Okay, so let's call this here the fluctuation determinant, and this depends on omega and t. And actually, we just okay, make one comment here already. So why did I want to write it this way? Because there is still some, let's say, some normalization factor here, which can be hidden in this measure. There's some normalization factor which came from the function integral, and there might be some factor from making the change of variables, so there can be factors 2 and whatever appearing. Now, we can use what I said last time, so it's good to have like one reference path integral that we did explicitly, which was for the free particle. So this means that this is a fluctuation determinant that depends on omega and t. Now if we set omega to 0 here, we immediately see that this is an expression for the free particle, no? So it's free particle. So we can always fix in the end the normalization by demanding that setting omega to 0 gives us a free particle solution. So we don't really have to care here about this normalization factor, okay? So this simplifies everything a bit. So let's then do once in very much detail consider this fluctuation determinant. So first, we can use the fact that, well, here we still have a sum with a product, but this is just again a product over an, so we can organize all this as a product of integrals over an, you know? So we can write this as the product, then we have just some infinite product of Gaussian integrals, this form here. So if we look at this integral, well, we know that gives some prefactor, and then what we always get is the inverse of the square root of this number here, no? So we can just write this, this will give some normalization factor, which we can call the contribution where we set omega to 0. Okay, so this is fixed in the end. This will fix in the end this normalization constant, which we can get by comparing to the free particle, so we don't care too much about it. And the only thing that we care here is the omega dependent part. And the omega dependent part will just give us here Yeah, there's some, exatamente, tem que ter omega squared should be in the end, I guess.
Multiplicando todo esse fator da exponencial.
Hã?
A n quadrado? Multiplicando todo esse fator da exponencial.
Não, o a n quadrado está faltando. Just, okay, got it. Okay. Just got confused, so this should still depend on n also. At some point I couldn't read my n, it looked like 4. So this is an n, this is not 4. Okay, so then we get the square root of this. 1 minus t omega of pn squared, the square root. Okay? So this is, from this Gaussian integral, we get some factor which doesn't depend on omega, and this is just the square root of this. Okay? So we get that all this can be written as a product of these factors. And now what we do is exactly rewrite this as a contribution which doesn't depend, like which would result from omega equals 0 plus or times contribution which results from looking at finite omega. Okay, so we write this as the free particle fluctuation determinant times now the part which comes from finite omega and which is omega t np squared to the minus 1/2. Okay, so this is just copying this, and these all factors we get into the normalization, which we will fix by comparing to the free particle. Okay. So this is like, again, just to make clear, so we wanted to calculate fluctuations of this term. What we did is we went to an eigenbasis of this operator. So we saw that these are the eigenvalues, and what we get here is just the product of the eigenvalues inverse square root because of the simple formula of the Gaussian integrals. Okay? So the one simplification which here is actually of much help is that we only care about here the omega dependent part in this compared with the free particle, and this is why it's good to have this calculated once exact. Now at this point we have to know how to do this product of this infinite product, and I just write down some identity. So this is an identity which I think, I think, like, I have, if I recall, like, kind of considered this kind of expression in functional analysis, where you use, I mean, the properties of complex functions, the complex plane, to show these kind of identities. I don't know if you also know this. So you can compare, like, you can compare, how would you do this? So, does anyone recall how you kind of prove these kind of identities? No? But you have seen them in functional analysis? Yeah? So, one way I think to see it is like if you compare the analytic structure. So you see that they have all the same poles. So you look at like what kind of poles you have in the complex plane, no? So you see that this is a product of many terms. So you have this in the denominator. So you see all these poles popping up at specific values of x. So whenever this is 1, this kills this one, and you have a pole, okay? And you see that the same kind of pole structure you have on the right-hand side. So you have two expressions which have infinitely many poles. You can look at guess the residuum at these places, and if you see like you have an analytic function which coincide on infinitely many points in the plane, then you have a theorem in functions analysis which tells you that these two functions are identical. So maybe I make an exercise out of it, but first I have to recall how you do it, but that's kind of the way I think. So if anyone knows how to do it, just tell me, because I don't really recall, but I think that's the way, no? Okay. So we can just use this kind of identity and then find, well, that the fluctuation determinant is given by expression at 0, for omega equals 0, which we get from comparing with the free particle, and then just this expression here, where now we can just look up from the last lecture the fluctuation determinant of the free particle, which is given by this expression here. So combining this, so we multiply this with this expression here, we can put everything under one square root, the t, for example, cancels, and so on, and then we have figured out the classical action. So we can write down here the result that we get for the harmonic oscillator. So collecting everything, we find for the harmonic oscillator the following result for the propagator. M omega 2p I h bar sine omega t square root, and then the exponent of the classical action, so I tried to fit everything here, which was I and omega 2h bar q initial squared q final squared times cotangent omega t, and then there was cotangent minus 2 q by q final over sine omega t. And now, of course, the set, so this has the form that you already knew, fluctuation, the classical exponential of the classical action plus the fluctuation determinant, and you can actually verify that this expression here is just given by the derivative of the classical action with respect to q initial and q final. Okay? So this is the classical action. If I take the mixed derivative with respect to q initial and q final, this doesn't contribute, because this doesn't have a mixed contribution, only this contributes, and you get like the 1 over sine, and okay, with m omega, blah blah, so you can verify that this is indeed of this form that we said here. Okay? So why did we do that? The entire exercise was exactly to one, see how you calculate the fluctuation determinant. And like we did use two tricks. First, we didn't care about this normalization factor, which can really be a pain. And this is always possible in the path integral in the end because we have some reference problem. So in the end, we only have to care about the omega dependent part here, this problem, and then so this was the first trick, separate this, and then the second, well, if we write down the classical action for fluctuations, then we want to just use an eigenbasis and using then the boundary condition. This in this case really simplified because we see the Fourier expansion consists of a discrete sum, meaning that the fluctuations just are the product, finite product of an infinite product of simple Gaussian integrals. Okay, so that was the one calculation exercise, and then we will come to the conceptual part, which is linking quantum mechanics and quantum statistics through the path integral. Okay, questions?
Is it possible to check this expression just by expanding to the first few terms? Let's say, to see if this is a Taylor series of, no, this one. To see if
What? Oh, this identity here?
That is, I was at Hatfield, they did it. It's just to put the logarithm, compute the logarithm of the left side.
So you compute like e to the log, you say?
No, you compute the logarithm.
Yes, but
so
this is like the idea. You say like the function is e to the log, so let's look at the log first, and you get the sum. Yeah. So you get the sum here.
Yeah, the idea is that so you modify the product, the infinite product, becomes infinite
Sum, yes.
and then you express this. At Hatfield have this.
Okay. So
if
that's
someone wanna go there at Hatfield page 288.
So this is actually that's like the usual trick you do. Like you can write a determinant of an operator A, which we are considering here, just as e of the trace of the log of the operator. Now this often simplifies exactly the problem because this product here over n equals to 1 then becomes a sum over n equals to 1 over infinity. So we get here a sum, but then you have to somehow do the sum of the logarithm, and you have to. It's also because then you have to care about the cuts of the logarithm, and.
But he uses he computes the logarithm.
Yes.
It's difficult to explain, but use an integral expression of something.
Okay.
In it files.
Okay.
But it's on. I cannot explain very well, but it's on Hatfield page.
Okay. Okay. Cool. So so maybe we will really look at this in the exercise. So this looks like interesting reference because I mean this is a standard thing that one does. It somehow looks more like the standard thing that one does. I always like these kind of arguments of just like saying, well, these two functions coincide on infinite points. But maybe I afterwards take the reference and see if we can do the next slide for us. More questions or okay. Okay, so now comes conceptual part. Quantum statistical mechanics, StatMech, and the path integral. So let me just very briefly recall like the basic things. We are interested in quantum statistical mechanics, and then we will see how this object is related to the path integral. So what one typically looks at in quantum statistical mechanics is a canonical partition function. Of a quantum mechanical system, and which is just given by what's called the partition function trace over e to the minus dh, where h is the Hamiltonian and beta is inverse temperature. And this object here is also called the density matrix. And also this is, apart from the normalization factor, the exponent of the Hamiltonian with one parameter which fixes the temperature is the density matrix. Okay, so this is, I mean, all of you know, familiar with, so this is like canonical partition function. So of course you have generalization, so this is like, you can see, well, that this is somehow related to the entropy, and you should get here the exponent of conserved quantities. So here we consider just a system where we have energy conserved, and there's one free parameter, like one parameter, which fixes the mean energy, which is temperature, and the inverse temperature. This is also called beta. What we are considering here is a single particle problem. Meaning where Hamiltonian for us, again, I just write down the 1D form. Generalization to higher orders is straightforward, is of this form. Okay, so the typical Hamiltonian, which depends on, has some kinetic term, a kinetic energy term, and then a potential, depending on the coordinate. Well, we can just write the trace, for example, as a sum over the complete state of basis of Q states. So there we find that D is given as integral Q e to the minus beta h and Q. So this here would be the matrix element of the density operator. Okay? So, but now if you look at this expression, well, this should somehow ring a bell, no? If we think about the propagator, what did we study so far? We always studied transition amplitudes from some initial to some final coordinate, and what we look at is the matrix element of the exponentiated Hamiltonian. However, it was the Hamiltonian here defines the time evolution operator, so instead of beta we have it over h bar. But apart from this, the object is very similar, so only here the initial and final coordinates are the same. So we are looking at, let's say, here transition elements from starting to the same point, and we look at the transition element of an exponentiated Hamiltonian, which now has a purely real coefficient instead of a purely imaginary coefficient. Okay, but still, if we define this here, then we notice that this expression here corresponds to the quantum mechanical transition amplitude from the initial coordinate, which we said here equals to Q, to some final coordinate which is the same in a time t, which now is given by t equals to minus I h beta. Okay? So if we set into the normal time evolution operator, where we would have this exponent. We said t equals to minus I h times beta. We arrive at this. Okay, so we can interpret the partition function as a sum over all periodic paths which connect, the one path, like periodic path, run through in some imaginary time minus I h bar. Okay? So this is actually something very strong and something that will also reappear later. So we just make the observation that the real time dynamics of a quantum mechanical problem is related to an imaginary time the quantum statistical problem of a single particle is related to a path integral if we accept that something like propagation in imaginary time is allowed. Okay, and this is a theme that will reappear, and we will make this more precise when we come to the quantum field theory, but let's just take it here as an observation that it is often very nice to think of time being some complex variable, okay, some complex parameter. If we allow so, we see that there is quite a deep connection between quantum statistics and quantum mechanics here of a single particle problem, but it also generalizes to quantum field theory. Of course, one should, if one thinks of this variable as some complex parameter, one has to like think about this is a function that depends on this variable, where is it analytic, how it's an analytic structure, but we'll come to this in more detail. Let's just here make this observation and see what we get from this observation. So the central observation here is that real-time quantum mechanics, or quantum dynamics, quantum dynamics in real time and quantum statistics, here all for a single particle problem, can be treated in the same way. By what I mean, this is for both we can formulate just a simple path integral. If we allow for imaginary or more generally complex valued times. So this is a very nice connection, which also at some time gives you some intuition about problem with quantum statistics. So you can relate it to what we learned so far about quantum mechanics in terms of path integrals. So, I mean, did you know this before? Like, probably who has heard about this before, or did calculation? Yeah. So as I said, so when we come to quantum field theory, we make this more precise, that we really look at the analytic structure of propagators and see how to, like, this is some analytical continuation, like this is a real variable which we want to make analytically continue to the complex plane, but you always have to be careful because, like a general function, can, like if this is like the real axis, and you have some function f from the reals, let's say to the reals, you can try to make this a function in the complex plane by allowing also for complex numbers, but you have to be careful because function of course can have cuts or poles, and then you have to be careful how to analytically continue these functions. Okay? So one has to have a notion about where cuts singularities of functions are if you want to make an analytic continuation. So here we are studying propagators where we want to make an analytic continuation. We will study their analytic structure afterwards in quantum field theory. Here we just take it as an observation to use then what we learned so far and write down a path integral representation for the partition function of the partition function. So we consider again a single particle, write down a single particle, consider single particle quantum mechanical system. And again, for simplicity, all here in 1D, but generalization is straightforward. Then we can write down the partition function as, again, an integral over all paths. So this is now using the Lagrangian version. So this is, we can write this as a path integral starting at Q and ending at Q. Now we integrate over all Q, so we write here this as an integral over all periodic functions, periodic paths. So we have a boundary condition that Q of 0 equals Q of tau. And I write now tau instead of t, so tau is used typically for the imaginary time. And what we have to do is, well, we have to sum all the paths and give every path now a weight, which is given by some s, which I call the action. Maybe I just write it. That now depends, that's the action in imaginary time. So this index tau here refers to imaginary time of the path divided by h bar. And the action of the given path is given by the integral integrate to beta h bar, integrate over d tau prime. You have a q squared over 2m. Now the derivative dot here is respect to the imaginary time, and then we have a potential d of q. Okay, so this is just what we get immediately if we would follow the same construction scheme that we used to derive the functional or the path integral representation for the quantum mechanical propagator. Okay, so you can just go through the same steps, dividing like a time evolution in a time beta now in small steps, and then inserting Another way to arrive at it is just using this observation here, that we, instead of talking about propagation in time t, we want to talk about propagation in imaginary time, and then for h beta. So we get here the integral over h beta, and now we have to look at like some things. So in the path integral, we had here for the propagator, we had here an is over h bar. So we get here a minus sign. This is one difference. The I is just absorbed because we are talking about propagation in imaginary time. So the dt prime with an I in front of it becomes a d tau prime. So this is like how we absorb this here. But now there's one crucial point which will become also important in another application, is that if we would have here the action, the classical action for the quantum mechanical problem, this would come as a with a minus, and also we have kinetic minus potential. So this change in sign is exactly due to this use of imaginary times instead of real times. So that is kind of an important observation that we will use probably in the next lecture to address some problems. So this is an important observation. Now one can arrive at this just so can be verified by observing this. So we want to formulate an integral in imaginary time. So instead of t prime, let's introduce I tau prime, which we then integrate to be h bar. And we have to substitute I tau prime by t prime by I tau prime, and dt prime, well, it's the same, but the derivative then prime. Okay, so if you do this, so this is the derivative here, no? So if you do this, you see you get like, the I gets absorbed here, now you get two I's, which gives you the minus, so you get from here, the I gets absorbed here, the minus comes up here, and well, the I gets absorbed here, so you have to change of sign here because the minus was pulled out here. Okay? So you get the relative sign change because of this I in the derivative. Okay? So this can be just verified. So, but this is a very nice expression. So it tells us that. Okay, I can wipe this away, no? You may want to verify it, or if you like, you can also once go through the construction as an exercise. Let me just write down the observations. So the quantum mechanical partition function is expressed here as a sum over now periodic path and these are periodic paths in imaginary time. And the time scale you look at propagation is set by the inverse temperature. By inverse temperature. Temperature beta. Okay? So, in a way, we'll quantify this, but if you look at high temperatures, you would expect some of the classical statistics should emerge. And this just means that you look at propagation in very short imaginary time. So in a way, you cannot travel too far in this path integral. You can think already. So we said that there's always a connection. So, okay, maybe just conceptual. There's two connections. So one connection that we point out here is between quantum mechanics and quantum statistics. Okay, this is by allowing for imaginary time. There's another connection which we already observed before, which is between quantum mechanics and classical statistics. So the path integral can be viewed as some integral. So quantum mechanics means zero-dimensional objects. The path integral represents the propagator as some integral over objects which are now 1D objects. Okay, and these are, so we have only numbers. We have said before, we have exchanged a problem with operators into a problem with numbers by going to one-dimensional higher. Okay, so there's a relation between quantum mechanics and the statistics of one-dimensional objects. Yeah? And this is general, so you have between d-dimensional quantum field theory and d plus one-dimensional classical field theory. There's two relations. Now, what we say here is that the time scale for the propagation is here set by the inverse temperature. So when we go to very high temperatures, the path, the periodic path, at some point should just get stuck. You don't have any propagation anymore because in a way you don't have any time anymore to propagate, and we will quantify this. But this means that in the high temperature limit, we would expect that this integral over one-dimensional objects should reduce to just zero-dimensional objects again, because we don't talk about path anymore, but like you don't have traveling in imaginary time, but you get stuck. And this is like how you see reduction from one dimension to the zero-dimensional object again, then would correspond to the classical limit. Okay, we will make this more explicit. So that's the first. This actually, what I just said can be quantified a little bit bit better in the following way. So we see there is a kinetic term which is given by e to the minus q dot squared. So the kinetic term suppresses path with high kinetic energy. Okay. So just one more comment. In quantum mechanics, we had here this oscillatory integral. Here we are now dealing with exponential suppression. So mathematicians like much more, these kind of integrals, because what we used before is we said, well, if this is a large number here in the quantum mechanics propagator, we have a highly random sum of random numbers on the complex plane, so they nearly give zero. So this all is somewhat more well defined in the imaginary time formulas where we have really purely exponential suppression. So we see that high kinetic energies are suppressed. So the kinetic term then suppresses the radius that a particle can typically propagate within a given time of, let's call it the radius of excursion in excursion or traveling in imaginary time. So it suppresses the radius of excursion of the particle. Okay, due to this e to the minus q dot squared 2m. So let's just make a very hand-waving argument and see what we can learn from this. Okay, so maybe let's just make 5 minutes break and then see what we learned from this, which will, so what we still try to do, I don't know if we make everything, so we want to make this connection, we want to use this representation to see how the classical statistical mechanics really arises, and then we want to use an application to look at the partition function of the harmonic oscillator by just applying the calculation that we did before to see that these expressions actually make a lot of sense. It's like just 5 minutes so I can get some more.